Right. Good morning, everyone. Can you hear me? Right. Yeah. First of all, many thanks to the organizer. It's been a pleasure to be here, and I enjoyed the wonderful talks and open discussions. And in that spirit, I'd like to share some thoughts on how prediction of stable materials can be accelerated with machine learning, and what I hope can be called rational design. Okay. In a few words, if you want to predict a thermodynamically stable material, you need to be able to effectively sample the configuration space and accurately resolve competing structures. So on the structure prediction side, strategies can be broadly divided into prototype screening. That's what's given us Materials Project, A-FlowLib, and other ab initio databases. Global optimization, and we've seen a number of exciting results obtained with evolutionary search, ab initio random structure search, particle swarm optimization, minima hopping, and so on. And the good old rational design. So we've actually had quite a bit of success making predictions using the combination of these three strategies and having them confirmed experimentally. Today I would like to mention a few standing predictions where rational design was a critical ingredient. On the interaction description part, most of us use DFT, but the use of surrogate classical potential energy surfaces has been around since the early days of structure prediction. And this idea has been gaining popularity now with the introduction of machine learning potentials. So what I will show in this talk is a few examples of stable configurations predicted manually. I will describe a couple of proposed synthesis routes for obtaining desired materials, LIB superconductor and barium tin 2 strong topological insulator, and show how to construct robust machine learning potentials for use in structure prediction and demonstrate a few practical applications. Okay, to begin, I would like to describe the case of calcium B6. This was one of the most challenging studies that I've done. At ambient pressure, calcium B6 crystallizes in a very simple cubic structure. Our prediction was that at fairly low pressures, it should transform into something more complicated. Well, when we loaded the sample, laser heated it, and collected the XRD data, we observed something that we simply couldn't explain. We couldn't extract any symmetry or cell parameters. So ultimately, we realized that it was a multi-phase sample. So we had to rely only on the evolutionary search to find the ground state. And it happened to be this beautiful tetragonal structure with 28 atoms per unit cell. And in fact, at the time, it was one of the largest crystal structure found without any structural input and confirmed experimentally. But this is not the end of the story, because when I examined the results of the evolutionary search, there was this local minimum near the global one, and it basically corresponded to this structure where one of these atoms in a 24-atom boron block moved from the edge to the middle. So I figured maybe we could just add an extra boron there. Well, that resulted only in a metastable configuration. But when I added the boron into every other block, that became so stable that it actually destabilized the stoichiometric phase. So in fact, this is a common trick in studies of boron-rich materials. And I'm willing to argue that no sane person would try to consider a 49-to-8 composition and would be able to find this ground state from scratch. So here, just manual examination was critical. So currently, we're looking at the lithium boron carbon ternary. As you probably know, it received a lot of attention about 20 years ago when Warren Pickett made the prediction that it could be superconducting at nitrogen temperatures. Well, we were quite intrigued by a recent report of a new compound by Pavlyuk et al. And when we examined the structure with DFT, it just didn't make much sense. First of all, the structure happened to be 0.8 EV per atom above the convex hull. And when we tried to relax it, the energy went down by 400 MeV per atom. So obviously the initial configuration wasn't quite natural. Well, since they reported the unit cell parameters and symmetry, we performed an evolutionary search under these constraints. And we did find a slightly better configuration, still very unstable. So it had a more natural crisscrossing boron-carbon chains. Then we just removed the constraints and approached the stability by another factor of 2, still far away. But in fact, the best configuration at this composition I created manually. I just recall that boron and carbon like to form this honeycomb sheets. So I just added the lithium, just sprinkle it between the layers, and we approached stability to within 100 MeV per atom. So frankly, I don't know what happened in that experiment yet. We're still investigating. So here's an example or our attempt to design layered superconductors. It's based on this predicted LIB material that I will describe in a moment. But the thing that you need to know about it is that it has this MgB2 type p sigma states, which means that if you mix this material with electron-rich metals, it might stabilize the structure. And what I did, I constructed these combinations by combining LIB block and MgB2 blocks, and calculated the energy difference between this ternary structure and the endpoints. So here, as you can see, for a number of electron-rich metals, the difference was negative. So this was actually done back in 2008, and the reason I'm mentioning this now, because recently I've re-examined this lithium vanadium B4 compound. I actually looked at the whole ternary, and it appears that this particular configuration constructed manually is an actual ground state and a thermodynamically stable compound. So it would be interesting to check if it forms. In terms of superconductivity, unfortunately, it doesn't have much chance of being MgB2 type superconductor. The point is that vanadium has so many electrons that you effectively just bury the states that are needed for superconductivity. It could be non-MgB2 type superconductor, but typically the TC doesn't exceed 10 Kelvin. Okay, so the next project I would like to discuss is on lithium boron. I have to admit that I spent probably way too much time investigating this binary, and I truly thought that I was done. Well, everything started in 2006 when Stefano Quartaroli and I realized that LIB in this layered configuration should actually be stable under pressure and exhibit a lot of desired MgB2 type properties. There was actually an unsuccessful attempt to synthesize it in 2010 by Laziti et al. And at some point, I just got tired of waiting and we synthesized the material ourselves. It took us quite a bit of time to interpret the result, but we showed that it actually forms and you can quench it down to 1 bar. I guess there wasn't much excitement about this material because early studies showed that the TC should be only around 10 Kelvin. So what now seems a bit more exciting is that, as Roxana Margina showed yesterday, is that if you treat the material with anisotropic Migdal-Liageberg formalism, the TC is considerably higher. And in fact, the highest TC is expected at ambient pressure. So that made me go back and reconsider the synthesis route and maybe adjust it so we can obtain this material easier. In order to do so, I have to explain what LIBX is. In fact, this is a really interesting material that was mischaracterized for decades. Its structure wasn't quite known until Worley and Nesper in 2000 realized that it consists of linear chains incommensurate with the lithium sublattice. So I simulated it as a series of these unit cells with different lithium boron ratios. And what I showed is that you can fit this formation energy with near perfect parabolas. And the bottom of this parabola is actually at about 0.9, in really good agreement with the experiment. But in fact, it also makes it a very unique material because it apparently exists in a small but finite range of compositions at 0 Kelvin. So typically you have this widening of the stability range due to configuration entropy. Here it happens purely due to energy. We just need to find these tangents from lithium to the parabola and from the boron-rich material, which happens to be lithium B3. So having reproduced the experiment, we also predicted that if you compress it, the bottom of this parabola moves towards lithium. And if you attempted to synthesize this layered phase, that does become stable when you compress LAB. LABX would remain in the sample in a more lithium-rich form. So regarding this material, we speculated that it will probably be prone to disorder because stacking fault energies were very small, and we could probably only observe the 002 reflection. So now I can just describe what we pieced together by analyzing experimental results. I cannot show you all the data, but I think this is the picture that we believe happened. So we started somewhere in this stability range, let's say at 9 to 8 composition. And as we compressed it, this material became metastable and eventually decomposed into the 1-1 stoichiometric phase with boron layers and the more lithium-rich version with linear boron chains. So once we decompress the material, these two phases remain trapped in their metastable forms. And in fact, we saw a clear sign that this LIB, the desired layered phase, appeared at about 23 and then remained in the diamond annual cell down to 1 bar. Well, obviously, if you work with diamond annual cells, you have tiny amounts of it. So I figured that we could possibly adjust the synthesis route by manipulating the starting material. So you see, because of this unique property that it can move in a finite composition range, what we could try is to delithiate it first. For example, you could just heat it up and make some lithium leave the sample. This would correspond to moving up this parabola into the metastable region. So that accomplishes two things. First, this material would be destabilized earlier when you start compressing your sample. Second, it is closer to 1-to-1 composition, so you would actually have a larger portion of the desired layered phase. So hopefully somebody will attempt this, because again, this would just test the validity of this prediction, whether we can really see the difference between isotropic and anisotropic treatment. So my final example concerns barium tin-2, which is a very interesting case. First synthesized in 2008, it received virtually no attention. But in 2017, we predicted that it should be a strong topological insulator with a wide 200 MeV bulk band gap. And our colleagues actually reproduced the material. Unfortunately, they got it only in trace amounts. And you can see why from this recent phase diagram. It's actually not even there. So it would be at 33%. You cannot really get it from the melt. So you end up with a majority phase of barium tin-3 and barium tin-5. So it's actually a low temperature ground state. So obviously, I try to see what happens when you raise temperature or pressure. Indeed, calculations confirm that this is a lower temperature phase because it's destabilized at 550 Kelvin. Pressure actually destabilized it as well, and it seemed like a dead end. But then I noticed that another phase, HP12, which is the C14 Lavey phase, actually becomes stable quite quickly, around 4.4 GPa. And this could be actually a blessing in disguise. We could load a sample with this desired composition, maybe laser heated, obtain this barium tin-2 material, and then decompress the cell. Now, barium tin 2 is metastable. So because of the apparent similarity between the two morphologies, this material could actually transform into the desired HP3 phase. So I've decided to include a slide just to better illustrate the point I made in our discussion a couple of days ago, that whenever we make predictions, we should also attempt to suggest a particular synthesis route. But there is a limit to what ab initio calculations can do. When it comes to kinetics, I simply cannot definitively say whether a solid state transformation from the Lavey phase to this phase is going to be more preferable than from the Lavey phase to the combination of these two compounds. So I would rely on the experiment here, well, provided that the idea makes sense in the first place. So if you have thoughts, I would be really happy to hear that. Okay, so now let me move on and describe our work on the development and application of machine learning potentials for structure prediction. First of all, many thanks to Chris Pickard and Richard Henning for describing all the challenges involved in developing such interatomic potentials. We've been playing with this for a long time, and by 2017, we actually came up with this protocol, how to construct representative sets so that neural network models fitted to these sets could be used in unconstrained structure predictions. So effectively, we just do short runs and collect representative data, basically configurations that are likely to be encountered in real searches. So now we have an automated scheme how to do it. The next step is actually convert the structural information into suitable machine learning input. And we do it with very well-known Beller-Perinelli symmetry functions. And when it comes to training our neural network models, this is the only place where we inserted some physics. So I just reasoned that if you, let's say, developed models for lithium and tin, and then decided to extend it to lithium-tin binary, you need to ensure that the description of the elemental systems doesn't change. So we designed a particular architecture that ensures that. So now we can do it to any number of elements, and we've developed about 30 models with an accuracy of roughly 10 MeV per atom. But you should stress that this single number doesn't really tell you much about the performance, because we can easily reduce this error by probably a factor of 2, but then these models would be unsuitable for use in unconstrained structure optimization. The point being is that there will be a lot of artificial minima that will mess up your search. So that's why we kind of balanced accuracy and robustness in our construction. Okay. Now, would this approach really accelerate ab initio search? Because you need to invest quite a bit of effort into constructing these models. So when you evaluate the cost, you need to consider the whole thing. That involves the generation of DFT reference set, model fitting, the exploration of the potential energy surface, and finally, the DFT check of viable minima. So basically, you need to relax them. A critical question here is how many minima should you consider? Well, it really depends on the accuracy of your model. You definitely need to consider a window that is at least 1 sigma. And keep in mind that the number of minima just explodes if you go up in energy. Of course, this can be mitigated somewhat by refitting your potential, but we prefer to carefully construct the model and keep it fixed during the exploration. So this is a rough breakdown for the cost between traditional and machine learning potentials. For traditional potentials, you don't need much DFT data. The fitting cost is quite small. They're very fast, so you can really fast explore it. But you may end up paying a lot of cost when you re-examine this collected minima. So when we looked around some 5 years ago, we couldn't actually find any statistics on this. So we performed a couple of studies, but I will just show you some practical applications. Even like half a year ago, we couldn't really find any examples of thermodynamically stable materials predicted with machine learning potentials, because the majority of potentials were constructed for elemental systems, and these studies either reproduced known ones or proposed metastable ones. So our study, I believe, was actually the first that identified a thermodynamically stable compound. We looked at the magnesium-calcium system because our collaborators at West Virginia in Aldo Romero's group were interested in exploring magnesium-based alloys. So what is known about this binary is that it has only one compound, the Lavey C14 phase. And in fact, the system had been screened with a high-throughput DFT, and I will come back to this in a moment. Nothing new was found. So we created our model, we shipped it to Aldo, and literally the next day he says, oh, we are seeing something interesting, a phase that is very close to stability. It turned out to be this monoclinic phase at 7-2 composition with 9 atoms per primitive unit cell. When I looked at it, I immediately constructed a slightly better, slightly more stable phase by doubling the unit cell and making it orthorhombic. So OS 36. We were excited because when we calculated thermodynamic corrections due to phonons, in fact, we showed that this phase becomes high T ground state. And just to give you a point of reference how well neural network agrees with the DFT flavor we fitted it to, so these are results with the LDA. So the LDA tells us that this phase is already stable and becomes even more stable as we turn on temperature. So this was quite exciting, but we really wanted to do a large-scale investigation to show that indeed this works in more complicated cases. So we turned toward this very complex binary lithium-tin. It has a lot of complex phases. We also looked at it partly because there had been 2 DFT-based studies that used global optimization algorithms, and they actually identified 2 thermodynamically stable phases at the ambient pressure. So we were curious if we could at least reproduce these results. So first, we constructed our model, and as I explained, we just expanded on already constructed lithium and tin models. So the resulting accuracy was around 10 MeV per atom, and we used about 6,000 structures to do the fitting. And this is a typical result of the evolutionary search and post-search analysis. So what I'm showing here is the distribution of local minima at the neural network level in red. Then all the minima within 20 MeV per atom were re-relaxed with DFT. And as you can see, there is quite a bit of crisscrossing, well, consistent with the accuracy of the neural network model. Well, in this particular case, the global minimum at the neural network level happens to coincide with the minimum at the DFT level. In fact, it happened in 45% of all considered cases. So after this, we calculated phonons for everything that was stable within 20 MeV per atom at the DFT level. And this allowed us to select further which compounds might be high temperature ground states. And then we re-examined those with DFT. So now I'd like to show you the breakdown of computational cost, which was frankly very surprising to me, because the model construction was only 2% of the whole computational effort. In fact, the majority was the exploration of the neural network potential energy surface. We believe we have a very efficient implementation, but because neural networks are so much cheaper than DFT, we just went wild and considered large unit cells and overall over 1 million configurations. So checking these pools of minima at the DFT level took about 8%. So this number I had to recheck because it just didn't make sense. So phonon calculations are really fast with linearly scaling methods. In contrast, if you consider fraction of these candidates, phonon calculations basically took us 1/3 of the computational effort. Okay, so what did we find? On this slide, I'm showing 3 panels. This is the convex hull. This is a collection of metastable minima within 20 MeV per atom to the convex hull. And this is ranges of stability as a function of temperature. So the color coding here is green points are experimentally observed materials. Blue points are previously predicted materials, and the red ones are ours. So we were really excited that we reproduced every single phase that was considered previously or observed. And we also found a new thermodynamically stable at 3:1 composition. So obviously this common composition had been sampled before, but this ground state was not found because it already is quite large. It has 16 atoms per primitive unit cell. I should stress that it happened to be below the tie line by only about 2 MeV per atom. But in this case, we're comparing structures of similar morphology. So they're BCC. In this case, there is a lot of cancellation of error. So we actually trust this number. And as you can see, it's consistent across different DFT flavors. So this plot is important because sometimes it's claimed that if we just have phases close enough to stability, maybe they will be stabilized by phonons. Well, we checked that. And in this actually a couple of thousand structures, only 3, I believe, had a chance to become stable under high temperatures. 2 were known experimental phases, and this is our prediction of MS40 that might be stable at very high temperatures. Okay, next we just took a closer look at this identified ground state, because as you can see here, it has a lot of common features with previously observed or proposed compounds. In fact, they all belong to the 111 BCC family, and we came up with a convenient way of labeling them, basically the number of layers between successive team layers. So this would be labeled as 344. This was not just convenient, but useful, because then we could do a sort of a cluster expansion. So just a quick comment that in principle, you could do a whole composition and export different decorations, but for unit cell sizes above, let's say, 20, it becomes a real computational challenge. So in this case, we focused on the most promising subspace, which is BCC 111. So we only included blocks instead of atoms. So we investigated what combinations of subsequent blocks were beneficial. For example, 3,4, 4,5, or 3,4,4, but not 3,3,4. So using these guidelines, we actually scanned all the sequences up to 6 stackings and identified yet another thermodynamically stable configuration, this monster. In fact, it happens at 19:6 composition and has 25 atoms per unit cell, primitive unit cell. Now that we knew about the existence of this stable compound, we tried to find it with our evolutionary research, and we simply couldn't. It's just very large, and it has a very unusual shape. And this example, again, stresses the benefit of re-examining your results and analyzing them rationally. So we also did the exploration of this binary under pressure. And as you can see from this plot, we reproduced all the previously proposed ground states above 20%, but below 20%, we actually significantly revised the proposed convex hull. So a lot of previously proposed stable phases were actually destabilized. And here I would like to put these predictions into context, because when it comes to structure prediction, complexity is everything. So first of all, it gets really difficult to find ground states as you increase the unit cell size. Between 1 and 10, it's actually more or less trivial. Between 10 and 20, you're supposed to find them, but it may cost you. Above 20, it gets really difficult. But also you need to pay attention to what is already known. So you could have known prototypes or unknown prototypes. So when it comes to magnesium-calcium system, in fact, what we discovered with our neural network-driven search were already known prototypes. So I mentioned that this binary had been scanned with DFT high-throughput screening. And I checked that at the time, these prototypes were not in the ICSD library, so that's why they were missed. In our case, we could have constructed them, but in fact, they were found automatically with neural nets. Now, what about the lithium-tin system? So the only ground states that survived our test that had been proposed previously are these small unit size phases at high pressure with just 2 or 4 atoms per unit cell, or ground states that have prototypes in related chemical systems. So our contribution is that by using neural networks, we actually identified considerably larger unit cells. Again, one could argue that they could have been found with cluster expansion. However, the real benefit is here. We found completely new morphologies through global optimization on the neural network level. And in my opinion, they could not have been found at the DFT level. In fact, the low symmetry here suggests that maybe we didn't even find the ground state, but we at least improved on what is already known. So in conclusion, my recommendation is to complement algorithmic search with just rational and intuition-based consideration. I've shown you a few examples that support my current viewpoint that we as humans can still compete against the machine at discerning stable patterns. Regarding the use of machine learning, you do need to be careful when you construct your interatomic potentials. In our case, we use a combination of evolutionary sampling and stratified training. We've shown that this methodology does work for alloys in the case of magnesium, calcium, lithium, tin. And currently we're finishing a study that involves 6 binaries, including tin. But as we move towards more complex systems, the current protocol might not be effective because as you lose accuracy, the number of candidates that you need to consider after you perform the search grows very rapidly. So frankly, I was very impressed by Chris Picker's results on silane because this is definitely a very complex system. And the fact that he found ground state with 60 atoms is super impressive. So with that, I would like to thank my group and many collaborators on the computational and experimental part and take your questions. Thank you.